Okay, hello and welcome to my channel. Today we're going to talk about the Levinson's theorem, and this theorem basically states that there could be infinite amount of bound state if your potential well is deep enough. So the general image I want to use to represent this theorem is something like this. You have a well that has bound states. And above the bound state, there are infinite amount of scattering states. And when you pull your potential down, when this gets down, those scattering states are going to get pulled in. So this is the image I want to use to simplify this Levinson's theorem. And the theorem stated that n is equal to 1 over pi the scattering phase shift when the energy is 0 minus the phase shift when the energy is infinite. And this guy is conventionally defined as 0 because, well, you can think of a giant rubbing earth and he would feel it as smooth as a cue ball. It's basically the same for this situation here. You just think that it would pass through undisturbed. Okay, so remember that. And it is a theorem, so of course we're gonna have to prove it. Well, and by proving it, we first have to imagine our scattering the 1D scattering with some potential up to R. Right, so this is your 1D scattering system, right? And what you want to do here is that you take this picture and you zoom it out. You zoom out. So as you zoom out, you would hope to eventually hit a wall. So I will draw this minuscule r. Small is these are the same. Zoom out. All right, and you want to eventually hit an infinite wall. Say at R. I mean at L. Yeah. At L, and this is very, very far away from this picture that we are considering back then. So say that L is a lot larger than R. So once you have this, you can start to count the positive energy states, and this would kind of act like an infinite square well. So now we're going to take a look at the two cases where your v of x is equal to 0 and when it is not 0. So first case, when it is 0, the positive, so we're going to count the positive energy states. And when it is 0, you have your phi of x sine kx. And as it goes to L, your phi of x is gonna, phi of L is gonna be sine kl. It's gonna equal to 0. Okay. So when it is equal to 0, get kl is equal to n pi. Okay, and from here, how do we count? Well, remember, counting means in physics, you want it to be easy, you take intervals of things. So, for example, there are like a lot of positive energy states here. You want to take an interval sample from here to here, and call this the interval dk, right? So this would be your k-space, and you take an interval dk, and from the up there you get that your dn is equal to L over pi dk. Right, that's the first one that we need. Now we're gonna take a look at the second case where v is not 0. Okay, so leave that there. Second case where v is not 0. Remember, we're still counting positive energy states. Now it is psi of x. That is ei delta. Ei delta. Wait, no, it is sine ei sine kl. Yeah, this delta sine kx plus delta. Okay, so now this is L. Just right away that this guy right here would be equal to a multiple of pi. Alright, so now we're gonna take intervals again, just like the one that we did over there, but this time is gonna be different. The number's gonna be different, so this is actually n prime instead. So from here you can write that dn prime equal to L over pi dk plus 1 over pi d delta dk. Here we go. So once you have that, now the total amount of positive energy states would be the dn minus dn prime, right? And when you take these two and you minus them, what you get in the end is the 1 over pi d delta dk. So this is what you get in the end, and from the fundamental theory of calculus, these two are the same thing. So you have proven the Levinson's theorem, and that would also be the end for today's video. Goodbye.